Hello, my name is Crispin Bonkum. This is my Math 116 project, Sequences of Number Theory. So just a quick little intro about my project. In number theory, a sequence is an ordered list of objects or numbers where each number is listed as a term or an element of that sequence. Unlike a set, which you've probably heard before, a set is just a collection of elements, whereas in sequences, it is also a collection of elements, but order does matter in sequences. And sequences can be finite or infinite. So just a quick, easy definition just to remember of a sequence is a list of elements in a particular order. Sequences have importance in mathematics. Where we study is where they can be studied as a pattern or puzzles. And then some sequences we will be discussing more on topic today are the Fibonacci sequence, the Lucas sequence, and the Dirichlet theorem, which also produces a sequence, which we'll get to more in the slides. So the first topic we'll be talking about today is the Fibonacci sequence. Just some quick history upon it is that the Fibonacci sequence was discovered in the early 13th century by Italian mathematician Leonardo of Pisa, whose nickname came to be Fibonacci later on. Fibonacci introduced the sequence to the Western mathematicians through his book Liber Abaci. Later on it was reported to have records tracing back all the way to 200 BCE in Indian literature. What this probably means that even though it was discovered by Leonardo of Pisa in the early 13th century, it was being used all the way back then in those previous times of 200 BCE. So as we can see, the Fibonacci sequence is the sequence of numbers defined by this linear recurrence equation, where the number in that sequence or term is the sum of the previous two terms. We can see that by f sub n equals f sub n minus 1 plus f sub n minus 2 with f sub 1, f sub 2 equals 1. And what that means is just that those are the starting points of that sequence. So we can look down below of the first 12 terms of the Fibonacci sequence. We can see that whatever element you're looking at that list, we can double check to see that it's the previous two terms added up. So for example, 2 equals 1 plus 1, 3 equals 1 plus 2, 5 equals 2 plus 3, and so on. You can see that it does follow that rule, and that also the sequence is infinite. And then down below is just a picture of Leonardo of Pisa. So these next two problems I want to talk about is some common problems that use the Fibonacci sequence, and that's the rabbit problem and the staircase problem. If you take in Math 145 here at Professional State with Professor Nogan, you probably have gone over these problems already and read them. But for the people who don't, I'll go over them in more detail. On the left side first, we'll start off with a rabbit problem. Fibonacci had considered the growth of an ideal rabbit population. In this population, there are three rules we assume. The first one is that a single new pair of rabbits, one male, one female, like we have at the top right here, are put in a field. Rabbits are able to mate at the age of 1 month, so at the end of the second month, a female can produce another pair. Third rule is that rabbits never die, and mating pairs always produce one new pair every month from the second month. So the puzzling question Fibonacci posed was how many pairs are produced by the end of the year? From the picture, we get just an outline of the first month to get an idea of what is happening. So we can see that from the first month right here, we start off with our rule number 1. A new set of pair of rabbits is put in a field. And then as the first months go by, they mature up. And by the end of the second month right here, they produce one new pair in the third month. And then as our third rule proposed, the previous rabbits never die. So then we get this new recurrence equation where, as we can see, the original rabbits never die and are always placed in the new months along with it. And then 2, they always produce a new pair at the end of the next month, at the end of the month they're on. So by the new month right here, we see they produce a new pair AB. And then we'll just focus on AB real quick. As we see, as we go to the next month, it still moves on to the next month, but hasn't produced a pair yet. That one moves on to the end of the second month right here, BC. But then as we look at it right here, pair A, each month it still moves on to the next month because they never die. But each month they produce a new pair of rabbits after the second month, because that is the rule that we must follow. So you can see it always keeps progressing and progressing, and that new pair will eventually make a new pair of rabbits as well as they mature. So then we can see that by the end of the 12th month, we look back at our previous slides right here, we could see the 12th term is 144. So by the end of the month, end of the year, I'm sorry, is that we'll have 144 pairs of rabbits. Then looking onto the problem to the right, the staircase problem, is that the problem imposes that you're climbing a staircase. It takes n amount of steps to reach the top. And for each climb, you can either, there's two ways you can climb it. You can climb one big step where you take 2 steps, or one climb is 2 steps, or you could take 1 step at a time. And the question is, how many distinct ways can you climb the top of the stairs? So we'll start off with an example, n equals 2, where our little buddy is on right here. There are 2 ways you can do it. You can either take 1 big step of the 2 stairs at a time, or take 1 small step at a time, resulting in 2 stairs. So there are 2 distinct ways of climbing up the stairs for n equals 2 for that problem. And as we look down at our problem below, we see that n equals are the number of stairs right here, and then the output are the distinct ways you can see how many steps they can take up these stairs. And as we notice, we see that these problems right here, or this table, represents the Fibonacci sequence. The n spot is just the element place, and then the output is the actual terms in that sequence. You can double check about that going back in the video to see if it matches up, but it does match up, just letting you know to save you some time. But I chose these 2 problems because they're commonly practiced in mathematics, because they're an easy representation of the Fibonacci sequence. Now, as Fibonacci is practiced commonly throughout mathematics, there is another pattern that represents the same properties as it. And that sequence is the Lucas sequence. The Lucas sequence was named after the mathematician Francois Edouard Anatole Lucas. Sorry if I butchered his name, but who had also studied the Fibonacci sequence. The Lucas sequence is made up of Lucas numbers, where similar to the Fibonacci numbers, each Lucas number is defined to be the sum of its 2 immediately previous terms. The starting terms of the Lucas sequence are L sub 0 equals 2 and L sub 1 equals 1. So we can see by this picture below, just to make it a little more clear, it could be denoted as if n equals 0, L sub n equals 2. If n equals 1, it is 1. And if n is greater than 1, it is the terms of the 2 previous ones added up together, denoted by L sub n minus 1 plus L sub n minus 2. At the bottom down here, we can see the first 12 terms of the Lucas sequences right here. And that's the same as the Fibonacci one. You can pause and check to see whatever term you're looking at is the sum of the previous 2 ones. And then just a quick note right here too, the sequence is also infinite. So just some relationship between the 2 sequences, because they're very similar to each other, is that they share the same recursive formula, if you haven't noticed already, where in which the nth term is the sum of the 2 previous terms. But the only difference they have from one another is the different starting points. Now, if you look down below this, I put down the Fibonacci sequence and the Lucas sequence. We're putting the first 12 terms of those sequences. We can see in the beginning, they both share some similar terms, such as 1, 2, and 3. But after that, the terms do not appear the same. The reason for this is because of the different starting points. So we can see how big of a difference it makes later on of the addition of having different starting points. Even though the difference is only just 1, it does make just a big difference as you're adding up. So just a quick exercise in both Lucas and Fibonacci properties. Since they are the same properties, but just different starting points, you can have a little fun with the recursive formula. So the property that we'll be defining is for each positive integer n, let L sub n equal f sub n plus 1 plus f sub n minus 1. So we prove this by using induction. We'll start with the base case with n equals 1. Then we get that L sub 1 equals f sub 2 plus f sub 0. After some substitution from our list, we get that f sub 2 plus f sub 0 equals 1 plus 0 equal 1. And then L sub 1 also equals 1. So our base case checks out. Now we want to assume this equation is true for n equals 1 to k. We want to prove that it's true for n equals k plus 1. So we look down this proof down below. We show our what to show. We do a little manipulation right here where we know how to find the Fibonacci terms where they're just the sum of the previous two terms, as we see fk plus 2 equal fk plus fk plus 1, and fk equals fk minus 1 and fk minus 2. We can do a little moving around manipulation of the problem to set it up in this way where fk plus fk minus 2 equals lk minus 1, and fk plus 1 plus fk minus 1 equals lk. And then just like the Fibonacci sequence, these two terms added up is the next term in the sequence, which we get lk plus 1, which we wanted to get in our what to show. So therefore, ln equal fn plus 1 plus f minus 1 is true for all n in the natural numbers. Now you can do more similar exercises with these numbers, but I just chose this exercise because it is the most basic out of all of them, just to get an idea to show how closely related they are to each other. Now the last sequence we'll be covering today comes from the Dirichlet theorem. The reason why I cover this topic will be brought up later on, but let us take the theorem. Dirichlet theorem states that if a and d in the integers are relatively prime positive integers, meaning that the GCD between those two elements a and d equal 1. Meaning they're both prime, as stated before. There are infinitely many primes of the form a plus nd with n in the integers. The equation in the form a plus nd form an arithmetic progression, and what that is just a sequence of numbers with a definite pattern. So for example, if you take the difference between two consecutive numbers and the difference is always the same as constant, then it is an arithmetic sequence. And the next slide, we'll look at that table with more examples to see what it actually looks like. Just some quick history about the Dirichlet theorem, that it was named after the German mathematician Peter Gustav Lejeune Dirichlet. And the reason why I chose this theorem to talk about in my project is that it relates to something we have heavily discussed in 116, prime numbers. I know we talked about prime numbers for a long time and are still talking about it, is that this theorem extends from Euclid's theorem, which we have proven stated that there are infinitely many prime numbers in the integers, or just in general. In Math 116 terms for Oscar, is that there are infinitely many primes that are congruent to a modulo d. And so we look down at these examples of the Dirichlet theorem. We can see that a and d are, for all of them, are two numbers that are relatively prime each other. For example, 2 and 1, 4 and 1, 4 and 3, so on, so on, so on. We can see that here, as we put in n for the numbers right here, we make a list of prime numbers. For example, we'll look at 2n plus 1. We see that the list is 3, 5, 7, 11, 13, so on, so on, so on. And then check to see that it is an arithmetic progression. We see that the difference between any two consecutive numbers in that sequence is the same throughout the whole list. For example, so 5 minus 3 is 2, 7 minus 5 is 2, 11 minus 7 is 4. So we can concur that that the difference between all those numbers is 4. And if we see the next one below it, 4n plus 1, we can see that even the it is also the same as well. There's just some differences. But you can be asking, how come there are some that are skipped? Is that because they're, for example, 4n plus 1, if you put n equals 1, you get 5. N equals 2, you get 9. But we can't put 9 in the list because it is not prime. So you have to consider that while making these this theorem, that the output has to be prime as well, not just a product of these two numbers. So as we look down these theorems, it further clarifies Euclid's theorem, saying that there's infinitely prime numbers. So we're just approaching the end of like a sequence. Just a quick recap is that Fibonacci sequence and the Lucas sequence share the same property where they're both recursive. And that is just that the only differences that they have is the starting points. And that, as we saw earlier, those starting points make a big difference, is what makes them stand out from each other. But in the end, they share the same recursive formula. And then just some applications of the Fibonacci to see how it works, and then applications of the relationship between Fibonacci and Lucas to see how they go hand in hand with each other, because they essentially are the same. And lastly, we covered the Dirichlet theorem and how the sequence that forms from it comes from an important topic we talk about in number theory about prime numbers, where prime numbers essentially is a heavy topic because it allows us to do so many things with number theory, for the fact that prime numbers have the GCD of each other, or just, or sorry about that, wrong thing, but if numbers are relatively prime to each other, they can form prime numbers. So that's an important fact we've been talking about. Thank you for coming to my project, and I hope you learned a little bit more about sequences of number theory.